So in this first video on the logistic equation, I'm basically going to be reading stuff to you and just talking about practical things. Very practical and slightly depressing things. Excuse me. Depressing in this way. Here we go. I hope you notice the subtitle. It's the end of the world as we know it, and I feel fine. Because exponential growth is seldom sustainable. If you look at population models for lots of things, if you look at like the census data over the last, well, through our nation's history, you're going to see a population that looks like this, and that's exponential. Can we always do that? No. The population of the world looks like that. Population of a lot of things looks like that. It's not always sustainable. I remember during the COVID-19 pandemic, they were talking about the number of cases, and I would see graphs in the newspaper and online. And notice I put newspaper first instead of online because I was reading the newspaper. But anyway, old technology. But after the printing press had come out, I subscribed to the first one. But anyway, this is the number of cases of COVID-19. Is it going to continue to do this and do this and do this? Well, no, eventually you're going to run out of people that get COVID-19. It has to reach a point with anything, population, number of people with COVID-19, whatever you're dealing with, where it levels off and it's going to start doing this and it's going to reach some carrying capacity. And here's what that means. This world can only hold so many people. There's only so much land to farm with. There are only so many resources. There's only so much carbon. There's only so much. You know, we can only sustain so many. We can't increase population towards infinity. We're going to increase towards some carrying capacity of population on Earth. I have no idea what that number is. I wouldn't even begin to guess what it is. Clearly in the probably tens of billions, but I'm going to just go with a random number. Let's say the carrying capacity of the Earth is 40 billion, which is packed pretty tight. But if we have 40 billion people on Earth, we just don't have the resources for more. So we would not be able to have just its continual increase. It levels off. So a few things that are good to know is that this idea comes from this statement. The rate of change of Y, population for example, with respect to time varies jointly. And jointly means we're going to have a couple things multiplied together. So we've dealt with direct variation, but we're going to really be dealing with like two things multiplied together. Jointly with Y and the difference of L and Y. We'll talk about it. There's a lot of letters going on here. So the rate of change of Y with respect to time, population or whatever, varies jointly. So there is a constant of variation jointly with Y and the rate of change of Y. Here we go. Oh, that should say Y right there, not a T. I will fix that in later versions of this. And so we're going to have Y right there. And the same kind of situation can happen here. It looks like these are different, and they are. It would change the constant of variation because you could divide both of these by L, bring it in the front. It's a thing you could do, not worth our trouble right now. But if you were to solve this differential equation, which we've done in previous lessons, it would lead to this. And then you're probably like, well, where did the B come from? And what is L? And what does it represent? And there's too many letters, and I'm already confused. And you know, I hear you. Person next door is laughing too. Apparently they think it's hilarious that we're going to reach some point where we can't continue to grow. But anyway, L is the carrying capacity. So here's what we have. The carrying capacity, the maximum, the population of the Earth or whatever it could be, is this. And in the formula, regardless of which one you're dealing with, it's going to be L. Generally, we'll start with either this one or this one. Those are generally the two that we have. We'll go with this. L is the numerator. So as time marches towards infinity, we reach the carrying capacity. So, 100 years from now, population will be up here, and then it's going to be up here, and then it's going to be, and eventually, if the carrying capacity of Earth is 50 billion people, 40 billion, 50, let's go with 50 billion people, then as time goes on, we're going to be like 49,997,000,000. And now I'm being a little more theoretical than actual. But it's going to really totter around that point, get closer to it. So as time continues, we reach the carrying capacity. The function is always increasing, and the rate of change is always positive. And these things are kind of common sense. But when you read them in a question, you kind of forget them. So the function's always increasing, Yeah, I knew that. And that means the derivative is always positive. So the derivative of this is always positive, which means this is the derivative. Either one of these is the derivative, and this is always going to be positive. Okay, y of t has a point of inflection. That's where the concavity changes. When y equals L over 2, that is half of the carrying capacity. Let's just start using this down here. When I've reached half of the carrying capacity, then I have a point where I am no longer increasing at an increasing rate. I am now increasing at a decreasing rate, right? So this is when the rate of change is at its maximum value. And you can kind of watch this with the tangent line. So tangent line, tangent line, tangent line, tangent line, tangent line. That's the steepest it's going to get, and then it levels off again. So that's when the slope is at its maximum value. Y of t, population, is concave up for all the y values, not t values, y values between, y values less than L over 2. So if you need to, you can put a little bit up here. You could say, this is L. This is my carrying capacity. And this is half of L. So we have concave up for these y values. We have concave down for these y values, increasing at a decreasing rate. And then a couple limits that are common sense, but again, good to see them. The limit as t approaches infinity of the slope is 0. Okay, t approaches infinity of the slope. So as this thing continues, the slope itself approaches 0. The tangent line begins to have a slope closer and closer to 0. The limit as y approaches L of the slope is also 0. Wait a minute. Okay, so now we're not saying, well, as we move forward, now I'm really saying as I move up, because this is the y-axis and this is the t-axis in this case. So as y approaches this carrying capacity, the slope is leveling off. So what I'm really saying is, if you move forward, the slope is leveling off. If you move up, the slope is leveling off. Those things are going to come in handy as we move on to the problems.